Okay, hello there. Today I am going to be showing you guys about chapter 8-2 called the reciprocal function, which is about hyperbolas, which is the name of the shape of the graph that you get when you graph these type of equations. So this is actually the notes you want to write down for the types of equations, and I'm going to teach it. Get my microphone over there. I am going to teach it like it's a transformation. So, but we've done a lot of transformations in this class where H is the horizontal shift, K is the vertical shift. H has a built-in subtraction sign in it. It is in the parentheses, even though there's actually implied parentheses in the bottom of that equation there, if you like, but you won't see them written down usually. So it'll go the opposite direction of what you'd think for the horizontal shift. The vertical shift will be exactly what you think it is. If I have, for example, if I had y equals 3 over x minus 2 plus 5, the vertical shift will be 5 units up. The horizontal shift will be 2 units to the left. And that would also be a stretch because it has the numerator of 3. And I'll come back and graph that one in just a few minutes here, just so you can see what it looks like. But that's the equation that we'll be looking at today, and I'm going to use the bettercalculator.com, which is like a graphing calculator, to illustrate some of this stuff to you, just to get the ball rolling here. So first thing is if I was to graph, for example, y equals 1 over x, I'm going to take a nice easy one so you can see a few things about it. Y equals 1 divided by x. Okay, so this is what the graph looks like. You can see it's got two curves. They also have two asymptotes. An asymptote, and I showed you this earlier, is a value that the curve approaches but never actually reaches. So you can see here along this x-axis, that curve keeps getting closer and closer and closer to that x-axis, but it'll never actually get there. Even if I zoom way out, it keeps approaching it but never gets there. And the same thing is true for the y-axis, and it approaches it two different directions. There's also this curve, which is also approaching the x-axis, and it keeps getting closer and closer and closer, but never will get there. So it's got two asymptotes, one vertical asymptote, one horizontal asymptote. And that's going to be, consistent throughout with these type of, equations where you've got the variables in the bottom of the fraction like that. Okay, so let's take something a little different. If I took that same type of equation, except instead of just having it y equals 1 over x, maybe I'll make it y equals 8 over x and see what that looks like. So I get the blue curves now, which means it's really very similar. It's just called a stretch. It's stretched more out into the first and the third quadrants. Let's say I change the denominator. Let me go back to the 1 in the numerator for a moment. 1 divided by x minus 2 plus 5. We'll do that. X minus 2 plus 5. Okay, so this is what you get. And you can see that, it's actually the same curves, but I moved them. This point here went like up 5 units and over 3. So this is actually the point right here. If you're looking at where the origin, the point 0, 0 moved, it moved over here. Which means that your two asymptotes would no longer be the x and y axis. Instead, this time, the horizontal asymptote would be, this goes through the y axis, so this is y equals 5. This would be the vertical asymptote, which would be x equals 2, okay? Which, no coincidence, comes from the 2 and the 5 over here. And we'll talk more about those things coming up in the next section. Okay. So what happens to my graph? Suppose I put a 0.25 in there instead of a 1. Let's say I have that same equation here, but Actually, I'll do this one. Suppose I took this one, and I made it 0.25 in the numerator divided by x minus 2, and then I got the plus 5 on the outside. See how it's very similar, it's just, this would be a compression where it's pushed down or pushed towards the center here where that, that 0.00 used to be. Now it's in the 0.25. So that's what the compression would do. So if I was to ask you to graph one of these things, suppose I gave you the equation, y equals 1 over x plus 1 minus 2, and if I didn't have a graphing calculator, I would pick some points and do it, but I know that I'm going to have these two curves, and they're going to be in these two quadrants, so if I was to graph it, y equals 1 over x plus 1, oops, I made a mistake here, y equals, I missed the equals, 1 divided by x plus 1 minus 2. Okay, so this is the graph. So the asymptotes, maybe you should figure out what the asymptotes are since you're looking at the graph. We'll do you try, hit pause, and then I'll come back and tell you what they are. Okay, we're back. So that vertical asymptote will be, the line going right through here. This is where it approaches, which is, x equals -1. So that'd be the vertical asymptote. The horizontal asymptote will be the horizontal line that curve approaches from two different directions, but never actually hits, which would be y equals -2. So those would be your two asymptotes. And if I was to ask you what's the domain of this function, there's x values for every single x on there except for that one right here is the only spot you're not going to have an x value. So the domain would be, all real numbers except x equals -1. That would be the domain. The range would be, there's y values going infinitely up and infinitely down, but there's not a y value for that one right there, -2, where that asymptote is. So the range would be all real numbers except y equals -2. Okay, so that'd be the domain and the range. And so let me go back to the other page here. Going back to this. Okay, so I already showed you this. Also, the vertical asymptote is y equals k. You can find that right there. And I liked this problem. I copied it out of the book, took a picture of it, and they're saying this is the graph up here. And it's a multiple choice question, which I know makes it a little easier, but it says, the graph of the function is the translation of y equals 2 over x. What's the equation for the function? And you got multiple choice questions here, and this is the graph. So I know it's already going to be y equals 2 over something. So if I start like that and start filling in the numbers here, the horizontal translation is going to be that much right there, because that's how much it moved up. All right, though you're looking at the asymptotes. How much did the asymptote move up? And this graph goes by 2's, which means that's 2, 4. So I got a plus 4 out here. And what happened with my y? Well, looks like it moved either there or there. It's the horizontal amount, which would be, looks like 3. And it's 3 to the left. So you'd think that would be -3, but this is the one that goes the opposite direction of what you'd think. So it really should be that one. So I'm looking at my multiple choice questions here, and it looks like A looks like the correct one. Okay, and that was the other thing I wanted to show you there. Okay, so I'm also going to start chapter 8-3 with you guys in this video. I'll finish it in the next video. This is on rational functions and their graph. First thing is I'm going to define a continuous graph for you. A continuous graph is one that has no jumps, breaks, or holes. And in simple words, it means if you can take your pencil and draw the graph and your pencil never leaves the paper, that's continuous. If you have to pick your pencil up for any reason because, you know, it's got any spaces in there, then that would be discontinuous, which is my second definition down here. I didn't actually define it for you. Discontinuous would mean you do pick your pencil up. So for example, if I was graphing this equation right here, you know, there'd be no way for me to draw those two curves without picking my pencil up. So that's discontinuous or not continuous, all right? And that's what that curve would look like. This one's different. This is a new one for you guys. That circle there has a hole. It's called a hole, okay? And we're going to talk more about this. But a hole means, you know, that line doesn't actually, I should have drawn this a little better, where it doesn't actually have that, the hole there. So if I went like this and drew it up, and then I get to here, and then there's that hole, and then this continues back through it. So that's not a continuous graph either, because, and you can tell that, you know, when x equals -2, that will make it 0 in the denominator and will make it undefined, okay? So this is an interesting one as well because, you know, I could simplify this, and this is why it's actually called a removable point of discontinuity, because I could cancel out the x plus 2's. However, the whole function itself is undefined when x is -2. And you can see that this line over here is real similar to y equals, you know, x plus 3. The only difference is that hole there. Okay, so it's not the same as y equals x plus 3, but it's darn close, all right? It's got that hole. So that's a new one for you guys, and you know, and that is called removable because of that. So the hole is removable. Okay, so there's a couple of introduction problems for you. So this is the first kind of problem I want to show you. I'm going to call it problem 1. And it says, what are the domain and points of discontinuity x and y intercepts? This is going to cover a bunch of stuff. What are the domain and points of discontinuity x and y intercepts? Okay, and the equation is y equals x plus 3 over x squared minus 4x plus 3. Okay, so first thing I would do, I need to factor that denominator. I need to find out what values are making that denominator 0. Okay, so there's nothing to do with the numerator, but I'm looking at, you know, what are the factors of 3 that add up to -4? You know, I'm going to have two sets of parentheses here. There's nothing in front of the x squared, so I can just put the x in the x. You know, and there aren't too many things that multiply to a 3. In fact, there's only 2 of them. It's either 3 and 1 or -3 and -1. And in this case, only these two actually add up to +4. So that's what I get when I factor it. So this is really the function that I'm looking at. However, you know, you'll have to do the factoring. Okay, so I got this. Now, the x-intercept is what you get when you take the numerator and set it to 0. Numerator equals 0. Solve it, you get your answer. Which means I got x plus 3 equals 0, and my x-intercept will be negative 3 when I subtract 3 from both sides. My y-intercept to find the y-intercept, you plug in 0 for x. Plug in 0 for x. So if I take that equation, everywhere there's an x, I plug in a 0. I got 3 of them, 1, 2, 3. And I can start solving this. So 0 plus 3 is 3. 0 minus 3 is negative 3. 0 minus 1 is negative 1. So I get 3 over 3, which is 1. So y equals 1 is my y-intercept. Okay. So points of discontinuity. So it's where would it be undefined? That's what I'm looking at. Undefined. Where? So I'm looking at that denominator, the x minus 3 and x minus 1. What makes those 0? Which means x equals 3 and x equals 1, okay? Take both things in the denominator, set them equal to 0, and solve them. Which means the domain is all real numbers except x equals 3 and x equals 1. Domain points of discontinuity and x and y intercepts. Okay, yep, good. Number 2. Y equals x minus 5 over x squared plus 1. All right, so this one, same idea, same directions. This one's different, and I can't factor that unless I use imaginary numbers. And if I'm looking at, points of discontinuity, there are none here, okay? There are no points of discontinuity in this one. Which means, and also, if I'm looking at the domain, your basic idea for domain is what are the x values I can plug in there? Or are there any restrictions on the x values I can plug in? And I'm looking at x in the numerator, so I can plug in anything I want into the numerator. There's no radical. Denominator, no matter what I plug in for x, it's going to be positive because you're going to square it, which means there's no way I'm going to get negative 1 after I square it because, unless you're looking at imaginary numbers, and that's not this. Those are special cases kind of thing. This one, there's absolutely nothing I can't plug in, so for x, which means this has all real numbers as its domain. Number 3, y equals x squared minus 3x minus 4 over x minus 4. Okay, so this one, a little different. If I go and factor this, I need to factor that numerator this time. I'm looking for things that multiply to negative 4, but add up to negative 3. So if I have either negative 4 and positive 1, or positive 4 and negative 1, that's the one that adds up to negative 3. So rewrite this. I get x minus 4 and x plus 1, which means because I've got the same thing in that numerator and the denominator there, that's going to be my whole. That is a point of discontinuity. And you should write whole at x equals 4. And is it removable? Can you cancel it out? Yes, it is. You could say that too if you needed to. Because I can cancel those out, that makes it removable. So I guess if you were thinking about it that way, those holes. All right, now, if I'm actually trying to find the whole, I need the y coordinate also, okay? So in order for me to do that, if I take the y equals x plus 1, because I canceled those out, and I took this 4 here, and I plug it in for x, I'll find the y coordinate, because it really is pretty much, remember, it's all very much like a linear equation. So if I get y equals 4 plus 1, which means y is 5, that means the whole is really at, let me erase that circle because you're not done. It's at 4, 5, and that is the whole. Okay, and the x-intercept. The x-intercept would be x equals -1. Because if I take that numerator and, the y-intercept here would be 1. That's really what I'm looking at with for what the y-intercept is. And the x-intercept, we'll do the x-intercept as a u-try. Why don't you try this right now? Okay, so y-intercept is where you plug in 0 for x, and I would get this here on the right, which gives me, these cancel, leaves me with y equals 1. It's also a linear equation. X-intercept, where you plug in 0 for y, these cancel again. I got 0 equals x plus 1. Subtract 1 from both sides. I get x equals -1. That would be my x-intercept. Okay, so I'm going to stop there, and we'll pick up more on this in the next video. See you all tomorrow.